This video will cover the basics of implementing a logistic regression classifier. I'll begin by outlining the core classifier components, followed by the mathematical intuition behind logistic regression. Then I'll discuss the sigmoid function, and finally I'll work through a case example of sigmoid classification. In general, supervised machine learning classifiers have four main components. They accept a feature representation as input, which is typically a vector of different values corresponding to characteristics of the input instance. They compute an estimated class using a classification function, and the details of this classification function vary depending on other aspects of the classifier. They compute error values associated with training instances using an objective function or loss function, and they try to minimize that loss using an optimization function. A logistic regression classifier trains a set of weights W and a bias value B using stochastic gradient descent as an optimization function that minimizes the cross-entropy loss. The classifier uses a sigmoid classification function and returns the highest probability label associated with an input instance. The goal in doing this is to build a classifier capable of accurately deciding whether a new input observation belongs to class A or class B. To make these decisions reliably, the classifier learns a vector of weights associated with the input features, along with a bias term. Each weight indicates how important its corresponding feature is to the overall classification decision. So, for example, some features might factor in very positively towards class A, whereas others might correlate negatively with the same class. The bias term is just a real valued offset that is added to the weighted inputs to improve the classifier's performance. To make a classification decision then, the classifier just multiplies each feature for an input instance X by its corresponding weight, sums those weighted features, and then adds the bias term. This function can also be represented using vector notation, which is useful since an input instance is generally represented as a vector of features. Now, multiplying feature values by their weights and offsetting the weighted sum by a bias term just results in a linear function of x. What we really want, though, is a probability ranging from 0 to 1. We can convert our linear function to a probability by passing it through the sigmoid function, which is also often called the logistic function, and that's why the classification algorithm we're talking about is called logistic regression. The sigmoid function of x takes the inverse of the sum of 1 and e raised to the negative x power. It's called the sigmoid function because when you plot it out, like what you see on the left here, it kind of looks like an S. The function produces a value ranging from 0 to 1. There are a lot of useful properties of the sigmoid function. Aside from mapping our linear function to a 0 to 1 range, it squashes outlier values towards 0 or 1, and it's differentiable. Differentiability is very important for learning how to optimize weights, as we'll see soon. Since we're working with binary logistic regression here, it's super easy to make all classes sum to 1. You just take the sigmoid of z for the positive class, and you take 1 minus the sigmoid of z for the negative class. To make the classification decision then, you just need to choose a decision boundary. For example, an intuitive boundary for binary classification would be 0.5. For your new test instance, the classifier will then assign one label if the computed probability is higher than the decision boundary, and another label if it's lower than or equal to it. We can work through a case example now to see what sigmoid classification would look like in action. Let's say we have a binary sarcasm detection classifier, so we're trying to decide whether a given input is sarcastic or not sarcastic. We have a small set of features that we're checking for. So for our input instance, we'll be checking to see if it contains the rolling eyes emoji, the happy emoji, and the unigram I'm. We're also assuming at this point that we're working with a model that has already been trained. So we have learned classifier weights of 2.5, negative 3.0, and 0.5 for our respective features. These values mean that the first and third features are positively associated with our positive class, sarcasm, whereas the second feature is negatively associated with sarcasm. So we'll go ahead and compute our feature values for this instance. It looks like the instance contains the rolling eyes emoji, but not the happy face emoji, and it also contains the unigram I'm. Again, since we're working with a classifier that's already been trained, let's say that at some earlier time we determined that the bias would be set to 0.1. So now we can go ahead and begin our computations. For easy reference, here are the functions to compute z, the linear combination of weighted inputs, and y, the result from applying the sigmoid function to z. With the values we have in our table, this means that to compute the probability of the positive or sarcasm class, we would take the sigmoid of our bias term, 0.1, plus the sum of 2.5 times 1, negative 3 times 0, and 0.5 times 1. This would be simplified to the sigmoid of 0.1 plus 3, or the sigmoid of 3.1. If we pull out a calculator and work that out, we end up with a resulting probability of 0.96. Remember, we're doing binary classification here, so figuring out the probability for the other class is super easy. We just take 1 minus what we just computed. So the probability for not sarcasm will be 0.04. That means that our classifier will select sarcasm as the output label, which, given the input instance, seems pretty accurate. A quick note about features. As we saw when we learned about naive Bayes, really anything you want can be a feature. In this case, we worked with a limited feature set where we just checked for some emojis and the word I'm. But if we wanted, we could have also considered other specific words, information from external lexicons, grammatical elements, part of speech tags, or any number of other features. A lot of times in neural classification models, the feature vector will also include word embeddings, which we'll learn about soon in this course. What we'll learn about really soon is how the parameters of a logistic regression model are learned using loss functions and optimization functions.